This is section 4.5, and this is on linearization, and we'll talk about differentials as well. We are going to approximate a curve by using a line. And in this box right here, linearization, it has this equation of the tangent line. And that's really all it is. It looks really fancy. But if we call this a and f of a, and we know the slope is the derivative of the curve, then we would have y minus y1, or f of a, and that would be equal to the derivative times x minus a. So that would be the point, and here we'd have the slope, and this would be the equation of the tangent line. But instead of writing y, they write L of x, the linearization of this curve. And they add over the f of a, they add over the y, and then plus f prime of a times x minus a. So that's where they get this equation right here, and we call it the linearization. And then we can use this line to approximate the curve as long as we're pretty close to the point of tangency. And you can see as we get farther and farther away from the point of tangency, the estimate starts to get pretty bad. But as long as we stay close, the estimate should be pretty good. Finding a linearization. Find the linearization of f of x equals cosine of x at x equals pi over 2 and use it to approximate cosine of 1.75 without a calculator. Then we'll use the calculator to determine the accuracy of the approximation. Now if we plug pi over 2 in, cosine of pi over 2 is 0, so there's the point. If we take the derivative cosine is negative sine. We plug pi over 2 in, it turns out that the slope is negative 1. So we have y, y plus 1, where'd I get, y minus 0. So y minus 0 is equal to negative 1 times x minus pi over 2. So that's the equation of the tangent line. This right here is the L of x. There's your linearization of the curve. Now we're going to plug in 1.75. So the approximation is this right here. And it turns out that it's negative 0.1792036. We can actually find out what f of 1.75 is just by plugging it into the original function right here. So we're going to plug it into cosine. Well, it turns out that it's actually negative 0.178246. So this is that's pretty close. And you know, we're approximating the value, and it's 0.0009576 off. So that's the error in the approximation. Approximating roots. So we're going to approximate the square root of 123. So we're going to make the function the square root of x. You know, we're taking the square root of 123. Now a nice one that's really close to 123 is 121. And the square root of 121 is 11. Now we have to find the slope. So we're trying to find the slope. So the derivative of this function is 1/2 x to the negative 1/2. Well, that sends that down to the denominator. And we plug 11 in, and we get 1 over 2 times square root of 121. That's 2 times 11, so that's 1 over 22. So there's the slope. Well, this is the linearization. That's the line that is approximating this function, but really close to 121. So we plug in 123. 123 minus 121 is 2. So add over 11, the approximation is 11 and 1/11. That's the approximation. Then in class, I actually showed the values. So 11 plus 1 divided by 11 is the approximation. Now the square root of 123 is extremely close to that. Differentials. Leibniz noted that you could split the differential, and he starts with this right here. dy is f prime dx, and so we're starting with y equals f of x. So if we take the derivative of the left, that's dy dx, then the derivative of the right is f prime of x. We're going to multiply by dx, so the differential, how y changes, is equal to the derivative times how x is changing. So if you want to find out how the individual variables are changing, then you do derivative and you can split the differentials. All right, so well, let me give you an example of kind of what we're talking about here. If we have, let's say, what can we do here? If we go from, let's say, 1 to 1.01, the difference, the change, the dx is equal to 0.01. And we're interested in from between this interval, how does y change? And if I draw the graph like this, y goes from here to up here. So there's a certain change in y. But if I make the line a little flatter, then y changes a little bit less. If I make it steeper, y changes from here to here a little bit more. So we're interested in when x changes by, let's say, 0.01, how much does y change? What is dy? To find that out, we take the derivative. So on letter A, it says find the differential dy and evaluate dy for the given values of x and dx. We're going to take the derivative. Dy dx is equal to 5x to the fourth plus 37. And then we'll multiply over dx. So the change in y is equal to 5x to the fourth plus 37, but then that times dx. And they give us the values for that. X is 1, so 5 plus 37 is 42. And then we're going to multiply that times 0.01, that's the dx, times 0.01, and y changes by 0.42. So when dx is 0.01, when x changes by 0.01, y is changing by 0.42. Letter B, now we're just going to do the same thing. So dy dx is 3 cosine of 3x. So we'll multiply over the dx, 3 cosine of 3x times dx. And so the change in y is equal to 3 cosine of 3 times pi. So they tell us x is pi. That's a pi, by the way. Times negative 0.02. Times negative 0.02. Well, the cosine of 3 pi is negative 1. So we get negative 3 times negative 0.02, which is 0.06. So y changes by 0.06 when x changes by negative 0.02. Letter C, the difference now is we have to do the derivative implicitly. So 1 plus dy dx is equal to first times the derivative of the second plus the second times the derivative of the first. So if we minus the x over and factor out the dy dx, we get 1 minus x, and then if I subtract the 1 over, we get y minus 1. So dy dx is equal to y minus 1 over 1 minus x. And then we just multiply the dx over. So dy is equal to y minus 1 over 1 minus x times dx. Well, now the derivative is based on y and x, but we only have x. So let's plug 2 in for x here. We get 2 plus y is equal to 2y. So if we subtract the y over, y is equal to 2. So really we have the point 2, 2. So we're going to evaluate this. dy is equal to 2 minus 1 over 1 minus 2, but then times the dx, which is 0.05. So 1 over negative 1, so negative 0.05. When x changes by 0.05, y changes by negative 0.05. Example 7, the radius r of a circle increases from 10 to 10.1. Use the linearization to estimate the increase in the circle's area. Compare this estimate with the true change and find the approximation error. So we're saying when we change the radius from 10 to 10.1, how much area do we gain? How much does the area change? So here's the area of a circle. Here's the derivative with respect to r. So dA dr is 2 pi r. Multiply the dr over, and now plug in the values. R is 10, so it's going from 10 to 10.1. So R is 10, and the change in R is 0.1, because we're going from 10 to 10.1. Now when we multiply all that out, it actually just ends up being 2 pi, because 0.1 times 10 is 1. So the actual change, if we take pi times 10.1 squared minus pi times 10 squared, it turns out it changes by that much right there. Remember, this is just an estimate when you're using derivative. But the accuracy is 0.0314. Now it says compare this estimate, find the approximation error. There's the error in the approximation, and use linearization to estimate the increase. See, the other answer is sitting right there. That's what we wanted. Estimating the Earth's surface area. Suppose the Earth were a perfect sphere and we determined its radius to be 3,959 with an error of 1/10 of a mile. What effect would the tolerance of 0.1 mile have on our estimate of our planet's surface area? So we could be, let's see, there's the surface area of a circle right here. If we take the derivative, ds dr, it's 8 pi r. Now we multiply dr over, and the r is 3,959, and the possible error, the possible change we could have is 0.1, so 1/10 of a mile. Now if you multiply those together, we could be off by almost 10,000 square miles, which I think the book says is roughly the size of Maryland. Exercise 1 through 6, find the linearization of f of x at x equals a. So we have a point, -4, we plug that in. 16 plus 9 is 25, square root of 25 is 5. There's the point. Here is the slope, and we did get that by taking the derivative. 1/2 x squared plus 9 to the -1/2, but then times the derivative of the inside. That's x over square root of x squared plus 9. We're evaluating that at x equals -4. And we end up with -4/5. So here is the linearization. That's the equation of the tangent line. Next exercise 15 through 22, find dy and evaluate dy for the given value of x and dx. So here we're going to take the derivative. 2 dy dx is equal to 2x minus first times the derivative of the second plus second times the derivative of the first. And let's see, what are we going to do? We're going to add this over because it's negative. Factor out a dy dx and you get 2 plus x. Then we have 2x minus y on this side. So we're going to divide by 2 plus x, multiply by dx, and here is what we're looking for right there. Now we're plugging in values, but we're only given x, we're not given y. We're going to plug 2 back in here for x and get 2y is equal to 4 minus 2y. So we add 2y and get 4y, divide by 4, y equals 1. So we have the point 2, 1. Plug 2, 1 in here. 4 minus 1 is 3. There's the 3 right there. And 2 plus 2 is 4. But the change in x is 0.05. So we plug 0.05 in, and we get negative 0.0375. Exercise 31 through 36, write a formula that estimates a given change in volume or surface area. Then use the formula to estimate the change when the independent variable changes from 10 to 10.05. So in 36, the surface area, the change in the lateral surface area S of a right circular cylinder when the height changes from A to A plus change in H and the radius does not change. In other words, we are holding R constant. So R is not changing. So it stays the same, but the height is either going up or down, and we're going to write the equation for that. But we're going to take the derivative, ds dh is 2 pi r, because remember that's all a constant now. So we multiply over dh, and we plug in what we know for h. Well, h would have been 10, but when we took the derivative, h is no longer in our derivative. It's not there. But the change is. So 0.05 is what we plug in for dh. Now 0.05 times 2 is 0.1. So this is the equation that they're looking for. Now if you have an h left, let's say it would have been h squared, then you'd multiply by 2 and h. You'd have an h to plug 10 in, but that didn't happen in this case.